Welcome. This is the talk on natural language processing, but today we are specifically looking at deep learning and transformers. Um, okay, so I'll start. My name is Mithun. I'm a PhD research scientist at the Data Science Institute, and my specialization is in AI and natural language processing. So I want to start with this question to every one of you, which is identify these famous people. Okay, I'll also keep an eye on the chat window here. Okay, does anybody have an answer here? You guys just can take a guess. Okay. Yeah. Brandon. Brandon says yes. Brandon says, is it a trick question? I don't recognize anyone here. Are they all AI? He got it right. So this is all AI, right? This is all AI generated people. They are clearly not famous. I was just messing with you guys. So the whole idea is these days you can create completely human looking people um, using AI, right? So welcome to your class on deep learning and AI. So today we're going to look at something called deep learning specifically. Uh, is, how many of you guys know about deep learning? Can I see a hand or where do I see hands? When I can't see my window again. All right. So like have you guys done anything with deep learning? All right, perfect. One person. All right, you have a rough idea. Okay, cool. That helps me a lot. So then I can focus on the level of details I want to get into. So you might have heard new all these names, right? Like Palm, Lambda, La, Llama, ChatGPT, all of it. Now the question is, how do they do all this, right? How are these models doing these supposedly magical things? If you had asked me this question maybe 5 years ago and told me here's an AI model that's doing really well, what do you think is the technology behind it? I will say, I don't know. It could be either computer vision, it could be natural language processing, it could be any of the subfields of AI that could have been driving it. However, now, if you ask me the question, what is driving deep learning? The answer is natural language processing. Most of the tasks, irrespective of whether they are visual or whether they are text-based, all is being run by a certain amount of natural language processing based AI models. Now, here, let me ask you this question. I went to the bank to blank. So fill in the blanks for me. Also, if it helps, it's easier if you can unmute because I lost track of the chat window again. All right, got it. Um, okay, so the answers are withdraw cash. I went to the bank to withdraw cash. Yes. I went to the bank to deposit money. Yes. You went to the bank to panhandle. That works too. But sure. Okay. I was going to give you this picture and say, what do you think it should be? And all of you said, okay, withdraw cash. Now, the next question is if I ask you, I went to the bank to blank, and I'm going to tell you, you cannot have anything money related there in the blank. What will you say? Well, I guess Randall already knowingly or unknowingly answered that, which is uh, I I was gonna I was looking for basically riverbank, and you're going to the riverbank to fish. But sure, you can come up with a lot of other examples. But this is my point when that even for you as a human, there was a chance that you could have said fish, right, instead of money. So how do you even tell this to a machine which only understands zero or one? right? So in short, irrespective of whether it's I went to a bank to withdraw some cash or I went to the river bank to catch some fish, the point is language is a hard task, right? So it is hard even for humans. So how do you expect machines to do so well? And yeah, they're of course doing really well, so we are not going to complain. So let's look into this. I want to start with the question now, how do humans learn a language? Imagine yourself when you were a kid. Okay, right. How did you learn? Like, what are the things you learned first? Okay, Randall says context. Okay, so when you were a kid, you completely understood. If you were given the context, you could tell what we are talking about. I went to the bank. Okay, reinforcement, comprehensible input, fair. Okay, so in reality, all of the above, right? So for example, if you have a toddler growing up, initially probably the child is going to understand here's a word called mom, here's a word called dad, or also we kind of have a mental model of, oh, this person is mom, this person is dad, and then you probably hear the word love, and then you say, oh, okay, hey, mom loves dad. And so if when somebody says mom loves dad, you automatically understand that, right? So we are kind of starting with the words and building up a sentence, combining them into meaning. And then we also learn from context, right? So for example, bank has two values, two more than two, what we call word sense disambiguation technically. But this is the ambiguity, right? So bank has two or more meanings. How do you learn that the very first time you ever encountered it? Probably it will be like, oh, hey, you always thought it was a bank, and somebody told me, I'm going to the bank. You always thought bank meant a financial institution. But then somebody told me, I'm going to the bank to catch some fish. So maybe for the first time, you made a correction in your neural network, neural pathway that, oh, by the way, bank also can mean river bank based on the context, right? So now the question is, we know how do humans learn the language, but how do why is it a hard task for computers? Okay, I think I was supposed to be keeping only the question slide there. But since I already have the answer there, I'll give the answer. So problem with computers is one, of course, we live in a continuous world. Our brain is more powerful than these machines. Apart from that, even when you think about it, you cannot just give them a random text. Say, I am hungry. What does that even mean to a computer who only understands zero and one, right? So they don't process information in the same way as humans do. So, or in other words, it's like talking to a baby. Like you need to understand the baby's language and explain it at the baby's level. So that means the text you're trying to input, you need to first think carefully how it must be processed so that your best way to talk to the baby, or in this case, a neural network, is probably dividing it word by word. And that is exactly what deep learning does as its first step. So in this slide, this is a school of thought which follows learning language from context. And this is exactly what natural language processing currently does. So what they do is, let's say there is a movie review, which is, I love this movie, it's sweet, but with satirical humor, etc. So somebody wrote a review. And now imagine the task we want the machine to do is, can you tell me if this movie review, that is a couple of these sentences put together, all sentences talking about the same thing, can you tell me what is the sentiment here? So, I mean, you as a human, when you read it, you understand, of course, okay, this is a very positive sentiment that the person who listened to or watched the movie was very happy with the movie. However, how do you tell that to a machine? The way people currently do is, let's take this whole paragraph, take each of these sentences in there, and we divide them into what we call tokens. You can roughly say like tokens are like words, almost, right? Sometimes are complicated ones where we have apostrophe s and stuff. But after all that processing, what we get is called tokens. So this is the very first thing we do. Let's break the whole paragraph into tokens. And now all it does is very, very simple. Like in fact, the entire neural network and LLM world, if you ask me, if someone asks you, can you explain in one line how LLMs work or large language models work? The answer is same thing that you do in Vegas, card counting, or in other words, frequency counting. That's all LLM does. So now what it does is, once you have these words, all of them, let's say in this case, the words are whimsical, satirical, adventure. Now, all they try to do is find out how many times does the word whimsical occur in all the sentences in the world. Let's say all the sentences on the internet, right? And then it learns that every time whimsical occurs, satirical occurs with it. So slowly, the machine is learning the meaning of whimsical based on the kind of words it occur with. So after hearing this, you all, assuming you all are humans and not a bot, you all should come up with another question right now. What would you do when I tell you that, okay, hey, it's very simple. LLM is just counting frequency. What would you as a human, your reply be? And let me make it more clear. What you as a human child learning a new language would tell back to the LLM. Any guesses? You, okay, now that we don't have an answer, you would tell the LLM, hey, but that's not how I learn. I kind of learn the meaning of the word whimsical first, right? The most common words are in the meaning exactly. That is what you as a person would be telling the machine. So that's a big debate. Nobody is complaining right now because this is working, but which explains why you need 3 months and tons of GPU, not to mention the flops and CPU cycles and the whole infrastructure and the carbon footprint it's generating, which is why fundamental architecture of the current neural network-based large language models is equally its boon and its bane. It's working, sure, because after seeing so many sentences, the machine has learned that the meaning of whimsical, it occurs with satirical. The meaning of bank is it occurs with money. And then okay, maybe this way, the meaning of bank occurs most of the times with money. However, there are times the second in rank when it occurs with river. So machine in a way currently is learning purely from what we call context. So of course, there's a history why this school of thought one was chosen, because the school of thought two was for the last 100 years, which we have been trying. Let's give the machine meaning. Let's try building it up together using this thing called grammar, just like humans do. And we got nowhere. So then people thought, okay, let's do a top down and see maybe this works instead of a bottom up. And surprisingly, it started working. So continuing on with how LLMs work, like I said, the first thing they do is tokenize. Then they start counting. Counting is, hey, so this movie is very scary and long, not slow, etc. So you go find how many times did the word is occur in the second review, in every single review. And as you can see, the review two in review two, is occurs twice. So you see what's going on, right? They're calculating these numbers and checking out which one occurs with what. And all they do is just, get these numbers as vectors, throw them in a, imagine that you're throwing them in a two-dimensional graphical space. And then the machine realizes, oh, by the way, vector of king, after seeing all the sentences on the internet, and the vector of queen almost always occur together. So they are even sitting next to each other. So this is currently what we call machine learning. So the machine is learning that queen can be created by looking at the vector of woman and adding to it the vector of king minus man. So give that a thought, right? Queen is a woman. Oh, but she's not a man's woman. She's the king's woman. Oh, so that's why it makes sense. So despite the fact that LLM is doing a top-down approach, they finally are able to tell the machine how human language works. And this was the first school of thought, the second school of thought, however you want to look at it, called, which we were trying for the last 1,000 years, sorry, 100 years, what we call the compositional, which is let's put these things together and all those dreadful grammatical signs, which we had to learn in middle school and high school, right? But clearly, even the LLM was a poor student like us, and they said, no, not going to learn grammar. So give me another way. We threw them mathematics, statistics, and LLM is pure, sure, that works. All right, so now the question is, what do you think are the typical challenges in NLP? Okay, in view of time, I'll probably answer this myself. So you already saw that text-based tasks, right? We have sentiment analysis. Like, can we create one of the earlier AI bots that showed up was, can you give me a sentiment of this particular movie? Especially the Amazon, especially when they were looking for all the automated ranking and stuff, that's how they were doing it. Classification, for example, is this email spam or is it a good thing? Classify each word in a sentence. What does it belong to? Can you extract an answer from a text? The list keeps going. You can even use it for machine translation. So that brings us to the question, sure, okay, so you roughly understand the language part. How does the actual bells and whistles work? So you're clearly not feeding this into an integrated circuit board as zeros and ones because it's doing some kind of magic, as these LLMs are, which, it's been almost 100 years since the first computer was invented, and we have never seen this kind of magic before. So clearly, you have done something different. So the answer to that is, it was around the same time that linguists were thinking of, hey, let's switch to a top-down approach, that another school of thought, not school of thought, a bunch of other scientists also came up with this idea that, can we try using neural networks? And you must be very careful when you use that word neural network, because what I just told you is, can I use my brain? Or in other words, the scientists, especially in cognitive science and a lot of computer scientists, started asking the question, if humans supposedly use neurons to communicate and also arrive at an analytical machine, can we create something known as artificial neural network? That is, can we use the computers to mimic the real neural network, which is the one that sits inside your head, right? So I'll probably take another 10 more minutes before we jump into the hands-on. Now, the question is, how do they do it? Meg was telling me this is an NLP class and I should not go into the gory math details of it, or even the computer science details of it. So I thought of this example. Here's another trivia question. Where do you see this sign almost on a daily basis? You can either unmute or you can put in the chat. Car dashboard. Okay, Laura, you were first. So what does it do in a car dashboard? What does the sign do in a car dashboard? What is it telling you? All right, speedometer, fair. In this particular case, this also is the cruise control sign, right? You might have seen that. Now, then I ask you the question, okay, so you walked into it, you said cruise control. So how does cruise control work? So the way cruise control works is you take something called expected speed, which is the speed you tell the machine that, oh, hey, I want you to be always going at 42 miles per hour, right? And then the machine looks at its current speed and realizes, oh, okay, maybe in this case, 41 is the one you set, and 42 is what the machine is currently, its current speed is. Machine, car, you know. So what the machine or the cruise control or the PLC, what we call PLC deep inside that, would do is it does this thing called back propagation. So all it tells back to its own controllers is that 42 minus 41, or in this case, 41 minus 42 is negative 1. So dear controller, reduce the speed by negative 1. And this process, if you have taken control system classes, you would have known this as back propagation at that time. It's feedback loop or whatever, you knew this forever, right? So all neural network does is exactly the same. Neural networks are a collection of software developed neurons. Let's put it this way. It's a blob, an executable, which behaves exactly like how a human neuron behaves. It has one head going out, two heads receiving input. If you remember the neuron picture from your biology classes, same thing and all the same functionality, right? And what is the functionality of neuron in a brain? So you might know that if you open up your brain and you don't see one neuron, you probably see trillions or 10 power 100, I don't know, Google amount of neurons. So that's when all this idea of using a software neuron has been around for almost a half a century or more now, right? But until 2012, people could only make one neuron at a time, connect them to two neurons, and then your hardware runs out of memory or your CPU runs out of processing power. But as serendipitous it might sound, exactly around the same time, the linguists were making a huge paradigm shift in their thinking. The hardware also suddenly started booming up. Maybe other way around too, maybe the hardware boom came first. But that's when all these computer scientists who have heard of neurons, or it was called perceptron, the computer science equivalent of a neuron, and they started thinking, wait, at that time, we had to give up on using the software equivalent of our neurons because we did not have enough hardware to support it. But now it looks like the hardware is supportive. We have huge amounts of processing power. Why not create trillions and trillions of these network together, and let's see if we can mimic what a human brain does. Even now, I don't think we have, despite all the GPT's huge model, I am still not sure if they have more neurons than human brain. I think we are still in billions and humans are still in trillions. So clearly, the more neurons you add, maybe more intuition level questions your model might be answering. But when this showed up, initially, the first thing people said is, okay, here is a neural network. Let's put all these in this order. Let's see what happens. Let's give it a task. Maybe, hey, here is the email. Can you tell me whether it's spam or not? And the neural network had no idea. It just started blinking randomly, right? And it said, the first email it said is, oh, yeah, this is spam. But then you, as a human evaluator, sits there and realizes, no, this is not spam. This is a genuine email. So you go back and tell that fact to the machine, just like the way we did 41 minus 42. So in short, between the expected value and the current value, the machine gave a wrong current value, and you are saying, nope, the expected value is not spam or ham, like we call it. And now the machine takes the difference in these values. I'll come to that in a second, but let's say the -1 is the difference, and it goes back and tells all its components, like the billions of neurons, yeah, all of you guys update your weight by -1. Not exactly -1, but still, it's roughly the idea. So you might now ask, but what is the difference between ham and spam, right? How do I say that numerically? The answer to that is, if you remember, earlier we have seen this interesting topic on, interesting picture on, what is thing called? There you go, Queen King Woman, right? So that one directly is responsible for the finding the difference. So all they do is project it into a two-dimensional vector, graph vector space, and then they decide, oh yeah, okay. So uh, this is the difference. So that is the difference between the expected value and predicted value. So let me back propagate that to these tons of neurons that are there in my system. Okay. Let's go back to what we are doing right now. So that's how, in short, in two, in the explain LLM in 10 minutes. And that's all LLM does. That's all neural network does. Or let me put it this way. That's all neural network does. And when people started throwing in the whole internet, instead of one or two emails for spam and ham classification, they started being called large language models. Especially, they have, since they have been showing all these amazing human-like abilities, that's why we are calling it a large language model, because it's different than regular language models because it's doing something special. So like I said, all it uses internally is artificial networks. And there's one more component. So again, another trivia question. Identify this movie poster. I lost the chat window. Okay, anybody? Do you know what movie poster this is? You can guess. What movie is this? Okay, Laura says Transformer, and you are right. Do you know which one? Yeah, okay. So clearly, even I did not know, but I think this is the latest on the Rise of the Beast, right? So Rise of the Beast basically, oh, thanks. Good, Bruce, you got it. Uh, so yeah, so Rise of the Beast, no. So the Transformers, this is the third component which gets large language models to be large language models. Remember, the first component is the artificial neural network. The second component is the language tricks which we have been doing. But that was 10 years ago. In 2013, we started experimenting with all possible combinations of neural networks, right? Do you want 10 in the first layer? Do you want 20,000 in the first layer? What is a good architecture to give it good results? Finally, almost half a decade of research later, we arrived at something known as transformers. The architecture, the neural architecture, the way in which you arrange neurons is called transformers. And the first model which came out with that was called BERT. So right now, you might have heard both these words before interchangeably, or if nothing else, you might have heard the BERT word, because every single big company in the world uses a large language model, and they all work based on BERT. So initially there were Bert, Roberta, Albert, then that was all like the open source community, and then OpenAI comes in and calls their one's GPT. But if you ask me, what do all these things have in common? It's just the same thing, transformers. They are built completely on transformers. Just that little architecture you saw, except, it's not little anymore because you will have 10 power, billions and trillions of these architectures, neuron architectures sitting inside one LLM. All right, so that's the story of LLM. That's how AI in a nutshell. It took exactly 30 minutes because the next question I want to ask you is, great, but how accessible are these AI models? The reality is it's literally on your fingertips. So this is the time when we close this up and we look at the Colab notebook. So Meg, did you say you will post the link to the Colab notebook? Okay, even if you don't have the link. All right, so I have an idea. Okay, if you can go to UA Data Lab, github.com/UA Data Lab. Let's start here. Maybe, oh, you had already posted it, is it? Okay, so you go to UA Data Lab, github.com/UA Data Lab repositories, look for NLP speech, scroll down to the README part, and here is the link to the notebook. Okay, so this is the Jupyter notebook which we will be using, and you might have to click on the Colab one because we have to run. If you all might be seeing a Colab kind of. Meg, can you post the Colab link? Let me see if I can post it. All right, this will work. Anyway, can you guys see my Colab screen?
Yes.
Okay, perfect. All right, I'm assuming everybody has access to this one way or the other. So the same slide deck is kept here, but the way we are going to learn transformers is in the next, let's say, 30 minutes or 20 minutes, we are going to use our own transformers. So remember, this is the godfather of every single large language model that has ever existed. It came out of Google. So first thing I want you to do is pip install transformers. So I'm assuming you all know what Colab is and how Colab works. If not, I will do this with you. So let's say I'm starting a new Colab notebook. Colab is this online laboratory where you can run Python scripts, right? Okay. So I'm going to start this and I say, okay, please, I'm assuming you are seeing my screen, which has pip install transformers being typed. You might have to put exclamation mark at the beginning because that is the way you tell the users that, not the users, tell the machine that we are looking at uh, a shell command, a bash shell command, and not a Python command. All right, so it's going to take you a few seconds while it does that. Okay, so it's probably downloaded transformers. So let's get another code block, and then we'll do from transformers import pipeline. From transformers, how does this know? Oh my God, AI. From transformers import pipeline. Okay, you can choose to run it, not choose to run it, that's okay. But I'm going to add a few more things. The next thing is I want you to create a classifier. Oh, this thing remembers. Classifier is simply, remember the text classification tab? The same thing. We are going to create a classifier which is actually going to do sentiment analysis for us. And the way you do that is you call pipeline because transformers have an inbuilt class known as pipeline, which will do, which will internally call all these transformer models. And what we'll do is we'll give them to, let's call it review, right? To movie review. So my first review is going to be, oh, I love this movie. It's fucking amazing. Okay. And second one is, oh, I hate this class so much. It's a movie review, I shouldn't say. I hate this movie. Oh, it's a terrible experience. All right. So I'm just creating two sentences, two random sentences, which just vanished from your screen. All right. So let's see. I'm just stating. I'm assuming you know all. You all kind of know a little bit of Python at this point. So the next thing is, how do I call? How do I initialize this classifier? The way you do that is it says classifier of reviews. Right. So I'm just saying, hey, initialize the classifiers, and this is the review you're going to work on. These are the reviews you're going to work on. Okay, so this was easy because immediately it said, oh, the first one is positive and the second one is negative, right? So that's it. This is your 4, 5 lines of transformers right on in your hand. But I'm sure that's not what you came here for, right? So sure, you really want to open this up for other purposes. So the way you do that is, remember, let's try mimicking what remember the three things which kind of led to the birth of large language models? One is the neurons, the huge hardware support. Two is the language support. And three was transformers. So we already saw that, yes, transformers work. They do an amazing job. So, but then this is all straight off the shelf for you. If you want to start getting your hands dirty, what you have to do is go into the language side of things and start thinking like how we were talking earlier. Let's say, what did I tell you was so when I was telling you, hey, if you provide a movie review to a transformer like almost 30 minutes ago, what was the first thing any of these neural network models or LLM models does? If it helps, this was from the slide which had a brown bag and which had a bunch of a paragraph of movie review there. So what was it doing? So remember, I'm not giving you a fish anymore. I'm teaching you how to fish at this point. Does anybody remember what was the first task any of these LLMs do? Okay. Tokenize, perfect. Yes, that is the answer I'm looking for, tokenize. So now, no longer we are going to give them the reviews straight into the machine classified reviews, but I'm going to now say, hey, I'm going to do each of these parts with including tokenize. Okay. So for which, by the way, the transformers itself have provided you all of these. So you can do from transformers import and what we call an auto tokenizer. That's it. Okay, please auto tokenizer. Now, the problem with all these LLMs are like auto tokenizer. It's when you ask import, all it is giving you is a big architecture, maybe 10,000 of neurons arranged in a particular architecture. However, it's your job to train how to tokenize it, right? And oh, you didn't think that coming. You didn't see that coming, did you? Because you thought you could immediately use someone's tokenizer. But then, the transformer group was good. They're like, hey, no, you said you wanted to do everything yourself. So here's the tokenizer architecture. You go teach it how to tokenize. Or in other words, you go train this model. Clearly, we have exactly 10 minutes left, maybe less. So we are not going to train tokenizer, but that is why we use something known as checkpoint. The checkpoint is what others have. Let's see what we can, there you go. I can check. Oh, wait, and the whole thing. I think you let me type. All right, so checkpoints are basically these architectures like auto tokenizers that someone or the other on the internet tuned on so many different things. For example, this one is fine-tuned on a data set known as SST. It says uncased because it understands only lowercase letters, or it doesn't matter for it, basically. And then this Dilbert is yet another architecture that was built on top of BERT. So that's it. So what you do now is you take these guys and say, hey, I want this particular tokenizer because I don't have time for any of this right now. So the next thing all you have to do is, let's say now we kind of, if you know computer science, we kind of declared and now we had initialized this tokenizer, right? We just created a class of it, object of it, and then we need to give it some task. And the task now is this tokenizer. Let's see if it even, I think anything Colab shows, right? Oh, perfect, it does. So this Colab is looking for, actually, damn, the Colab is filling it out for you. These are the expected arguments for tokenizer. In this case, I'll just do it. I'll just bite the bullet. All right. So these are things which I was going to type in. So you were going to give it the reviews that array we had created earlier, the list. You're saying padding is equal to true. And all that means is, oh, by the way, there are going to be multiple sentences of different length. I want you to add them up with junk values or zeros so that every single sentence has corresponding length as that of the longest sentence. And the only reason we have to do is we are using a discrete computer or discrete mathematics-based computer, and everything is a matrix multiplication. And clearly, if you remember anything from the matrix world, it's if you have to multiply even two vectors, they need to be of the same shape. And that's exactly what we are doing. We are just trying to get all these sentences in. The very first thing we do is get them all in the same shape. Truncation is true, which means is, hey, there is a word like thinking, right? And in this, remember, syncing is actually the word, but the token, or what we call the lemma for syncing, is sync. So it's asking, hey, can I truncate if if I don't have the whole word, or do you want me to make it sync, comma, ing? And I said, nope, just truncate it, I don't care. And what else? Return tensors PT, I don't remember that anymore. You can always you know how to Google this, right? Just go to Google transformers, auto tokenized class, and it will probably take you to the documentation of this auto models, and you can find the argument that's going in there, right? Or there it is, auto tokenizer, should be somewhere here. Anyway, coming back to what we were doing, so let's see. So we just gave them the reviews, and we called this auto tokenizer, which is already been tokenized. We are going to ask it to tokenize these sentences. Okay, perfect. So it came back with a bunch of these numbers, which are just unique IDs assigned to each of these tokens. Because remember, now the machine does not call them words anymore. It's just tokens for them, or memory locations, right? So next thing we want to do is we want to use a model to classify it. So remember, the model which we use so far is auto tokenizer. Before, everything else here was ready-made off the shelf, so we did not want to use that. So the next thing what you should do is we need to get a model, and we can ask transformers, hey, give me some model, and transformers will tell you the same thing. Do you want a trained model or an untrained model? And in fact, by default, it gives you an untrained model. Same case is auto tokenizer, right? What is the meaning of auto model? It's basically, remember I was telling you there are these things known as transformers, the little small neuron combinations, which of course is also the name of the class we are playing with. Now from transformers, every time you do import auto model, it just gives you a huge architecture of neurons, 10 power 9 neurons, and have been arranged in a particular architecture You don't even need to know. The scientists went through it and found that this is the best architecture for something, right? But then they are telling you, I'm not going to tell you how to create a large language models or train it. I create a large language model for you, but I'm going to train it. I'm not going to train it because be careful for what you wish for. You might just get it, right? So now it's your job to do the same thing as earlier, right? We use someone else's checkpoint. And in this case, the only difference is we will have to call it model, and instead of auto tokenizer, we'll do it automated. All right, let's start this going because it's going to take a while. All right, perfect. So this model has now been initiated with a trained model, which was there already in the repository of Hugging Face. Oh, I don't know if you have been introduced to Hugging Face. Hugging Face is the mother of all large language model development, now at least. So this is where you go for any of the open source models, open source data sets. You name it, you'll find it. So I highly recommend going through Hugging Face. And if you're interested, we can do it sometime in this class. But coming back to more of the NLP side of things, so we already have a model that has been loaded with some of these previously trained things, right? So now all we have to do at this point is run the model on the reviews. Now, how do we do that? All you have to do is model, you're creating the model, right? And let's call it output model star review. What did we call that? Reviews? Reviews, yes, right? Let's see what that happens. Or in short, we are providing, what is this? What did I miss? All right, let's do it directly this way. Oh, yeah, okay. Just gonna use it. They have a different format for the list. I'm just gonna call it list. Oh, actually, we missed a step. Okay, let's see what this model does though. So star star. All right, so before that, the model we had downloaded is automodel.from pre-trained, right? But that was the catch. So how do you know this particular auto model is tuned particularly for this task, which is classification, right? So in fact, what you should have been doing is from transformers, import a model for classification because that is the one which is specifically trained for this task. The auto model one would have given you just some random model, but we don't want a random one. We want the one that's trained for classification. So let's call that guy first. All right. So now we have a new model. So now we already trained the model on this stuff, right? So now our question is, what we want the model to do now is it ran through the basic, all these inputs, and now you're saying, hey, give me the shape of what do you think is the answer to my question? Remember, the answer to the question is, I have two sentences, which is I have been waiting for a Hugging Face course for all my life, of this are the sample sentences. And I hate this so much. The question is, what is the sentiment of this? And remember last time when we ran the off-the-shelf model, it cleanly told you, yeah, the first one is positive, second one is negative, and I know these with a 99.99% confidence. But this time we wished, let's do it ourselves, and the model says, oh no, this is all I do. You ask me for my predictions, I'm going to give them these values, which is first class, which is the first sentence. There are two classes we are giving it, and we are asking, is it positive or negative? And it's giving me, hey, for the first class, I think this with this confidence, I think stat is negative, and for the positive one, I'm going to give a different confidence. Long story short, none of that matters to us unless you use a function known as softmax. You can read on softmax. It's basically pushing everything to between 0 and 1 and asking it to give a decent value, right? And now, if you really want like the English text, you probably will have like just do uh, this is again the same confidence level. I'm going to call something known as model.config.id2.label. And what that does is it's, it's already taken the 0 and negative, right? I already told it that. And now all you have to do is, so remember, I'm not training a model. I have only initiated the model so far. I haven't told it to do anything. It's initiated. And now I'm giving this each of these questions a raw input. I think that should understand raw inputs. And I'm asking it, hey, I told you, raw inputs, raw inputs, raw inputs. Raw underscore inputs, where did you go? All right, there you go. So now we ask the train model, dear model, now can you do all these things and tell me the two sentences which I gave you, are they, what sentiments are they? And the machine says, oh yeah, the first sentence is positive, second sentence is negative. Okay, let's see. We can say that I love this class, I love this class, and I hate this class. So remember, I said the sentences don't have to be same length because the movie reviews almost never are going to be the same length. And it still says, oh, I love this class, I hate this class. So now let's try tricking it. I might or might or not like. So now currently, that's the first step. All right, so it's still doing fine. If we go back and let's see if we can print the, probably the, okay, if we take the output and print it, you will be able to trace it and see that initially it would have given things like, hey, 99.99 confidence for the initial sentence, which was, I love something. But then when I made it a little bit complicated, what you would have seen is you can take this, you'll see that this value keeps dropping. It'll be maybe zero point 0.7 positive, and it's almost saying, yeah, I still think it's a positive sentence, but I'm not sure. So which is how we look for like, hey, zero point 0.7 it means the machine is losing its confidence. Long story short, between the slides today and the Colab workshop today, you have a big beast in your hands, the transformers. Just go Google transformers and Hugging Face, and the world is a playground. You will be surprised at the sheer amount of things you can just do with transformers and Hugging Face alone. All right. Any questions, anybody? Yeah, okay. So Bruce, I just saw a question. When you picked a transformer model, did you specifically look for the one tuned for classification? First time, no, because I wanted to show you what auto model is. And I just picked something which was, hey, auto model, you can use this version of transformers. But that auto model was not particularly trained for this classification. But next time I told it, so I wanted you guys to show you the wrong way of doing it. Not wrong. You know, we can even try, we can probably want to go back and try this with that model. You'll see that probably its outputs are not exactly zero point 0.9, or it might not be doing a great job in sequence classification. So which is why we went and called this guy, which is, hey, I think it's auto models for sequence classification. So yes, for this particular task, you should use sequence classification. And the truth is, at this point, there are so many tons of models that's already been trained on so many different tasks. There is a very high probability that the task you're looking to play with has already has a model specifically trained for it. Because remember, training these models are very expensive. Um, Okay, so any more questions? Well, if not, thank you. Uh, Thank you for listening to this class, and hope you had fun. All right, there's a chat, question. Okay, thank you.